Okay, so let's start. I cannot see my slides. Sorry for that. Okay, thank you very much. So the major topic of this talk will be living in eventually consistent reality and what this really means. We will be talking about systems that are scalable in terms of planet-wide scalability. So things like scaling our databases or systems over multiple continents and how all of that actually works underneath. So, well, we already been introduced. This is me and my contact links if you want to talk with me afterwards or afterwards. So what we will be talking about? We will be talking about specifically about the CRDs, so conflict-free replicated data types. We'll see what problems do they solve, what are existing solutions, so we don't need to create everything from thin air by ourselves. How do they work? How to optimize them? We will also talk about different notions of time as, let's say, side channel of this talk, because when we are talking about globally consistent systems, the notion of time and the differences between time zones, time clocks, and so on are starting to matter. So without further ado, let's take some case study. So we will nest our example somewhere in the real world, right? So we are going to build a YouTube 2.0 in this case. We'll cover specifically two different use cases. One of them is video streaming itself. So let's say that Alice wants to upload some video to be available to watch for the people all over the world. So when she's going to send her video, it's being uploaded to some server anywhere. In this case, let's say it's somewhere in Ireland, right? Now, if we would like to stream this video for potential millions of people all over the world, this might be a problem because we have a single server that have potentially high load, which could easily be taken down, and it could quickly also become a bottleneck. So what should we do in this case? The simplest solution here is to simply replicate that video to different continents potentially, just to maintain higher availability, so we don't have all of our data in the single data center. So even in the case when this data center goes down, we still have the high availability. So our video is available for people from other zones. Also, this allows us to reduce latency. So simply it's available faster, quicker for other people wanting to watch it. However, this is only one of the cases. The second case is a little bit different. Let's say that we would like to add a feature that is quite popular in YouTube, known as video view counter. So we would like to see how many people seen that video already. Now, this is kind of a different workload because this is logically a single number that is available to see by everyone, but also it's incremented every time the person sees that video, right? So it's not like a single person trying to upload the video. It's very different work pattern here. Now, this is even more interesting because while uploading the video is pretty easy, right? We have a single person upload this video, replicate it on the multiple servers. How to integrate this single view counter that could potentially be updated on the servers on the different continents and so on. How to make it work fast without risking the availability of our servers, because synchronizing this number across different continents is a challenging task, and we'll talk about why later on. But for now, let's think about other properties of that use case. For example, if you know how YouTube view counter works, you've probably noticed that it's not immediately consistent. It's something that we call it eventually consistent, which means that we don't know exactly the number of people that seen this video at any given point in time. This is something that is more or less true. Once people will stop, looking at this video and the updates will stop appearing, we will eventually get to the correct value. But at the time being, as people are watching it, what they are seeing in this view counter is more or less an approximation. So something that will eventually be true, but it's not exact value at any given point in time. So even though those people are seeing those view counters, at any given point in time, the value of that view counter might be different depending on which server did we ask for to get this value. And this is something that CRT turns out to be great to deal with. Because what they allow us to do is to synchronize that data safely without need of reaching any kind of consensus. It means that any of those servers could have potentially update their replicas by their own and synchronize with each other eventually to reach the correct value, but they don't need to do this right away. So we don't need to spend the time on, dealing with the potential conflicts, latencies, or trying to avoid these conflicts, actually. So this is where the conflict-free replicated data types comes in. And since there are existing solutions, but we will need to dig a little bit deeper down here, because one of the problems that you might find when you will try to play with them is that conflict-free replicated data types are not usual data structures. I mean, they are not like data types known from SQL databases, for example. They have specific properties that might not be intuitive if you don't really get the grasp of what they are trying to achieve. And basically, CRDTs are consisting of two parts. One of them is the data structure itself, and another one is the replication protocol that is supposed to handle those replication of the data types. And there are multiple different ways to solve the same problems here. And depending on the type, on where do we want to, put more pressure, either on the data structure side or the protocol replication side, we might find that different solution will have different performance characteristics. Today we will be talking mostly about this first point from here, I mean state-based replicated data types. And we will also tackle a little bit about state delta-based, because this is an optimization over the first case. So there are many other use cases here. One of them is synchronizing data over network with large latencies. This is why geo-replication is so great example for CRDTs, because when we are trying to send data across the continents, the lag or latency between those is much higher than when we are trying to replicate the same data between two machines sitting in the same data center. Another common example is any kind of mobile devices and things like chat applications, collaborative text edition, edge computing. Edge computing is basically, let's say, a cluster of services where each service is built in the client device. So we have multiple clients connecting together with each other instead of connecting with central server that is responsible for handling all of the operations. So basically anywhere when we want to synchronize data, and also we would like to be able to process this data offline as well. Okay, so there are many existing solutions in this area. One of the most popular ones are REAC, which for example is used by British healthcare public services like NHS. Another one is Amazon DynamoDB, which was one of the first one on this field. If you are looking for Azure, there is a Cosmos DB, which by itself does not provide these capabilities that we will be talking about, but it has protocol. It allows you to create enough space to create something like that on your own. And this will be also the case that we will be talking about here, because the examples that we'll be tracking with will be presented in JavaScript, and using Azure Cosmos DB, we have this option of so-called multi-master replication, when we are basically creating a stored procedures written in JavaScript to resolve the context for us. And this is a really great example on how to apply the things that we will be talking about here into real-world scenarios. There is also basically two shameless plugs of mine, because there is an application layer that allows you to build CRDs, which is called akka, distributed data. This is a plugin both on the JVM and .NET library, and I was one of the people who were involved in this area. And also Ditto Live, which is a startup I was working in the past, which is also why I'm pretty much be able to talk here about, which is providing the SDK for mobile clients. So basically you are creating an interconnected distributed database on the mobile devices and so on. Okay, so let's go further. So here we will cover the idea behind the CRDs. So how do they work in reality? In this sense, you will be able to create your own CRDs and, for example, push them on this Azure Cosmos DB service, or even tackle with them locally on your machines. And as I said already, those examples are made in JavaScript, so you could potentially create something like Node.js application, or even an Electron application running on the mobile device that will be able to make use of them. So first and first, it is possible to. We were talking about eventual consistency. So state when those systems are not consistent right away, they will be consistent eventually after our updates will be replicated. But it is still possible to achieve strong consistency in this scenario, just not in the same way, not in the same performance characteristics that we are usually talking about. So let's say that we have, for example, a cluster of 3 machines, 1 leader and 2 followers. This is a so-called leader cluster based on the leader election. So one replica acts as a leader and it can serve both writes and reads, while followers only will offer ability to read the data from their own logical copy. So in this case, when somebody wants to write or update the state of our application through this leader based cluster, whenever it contacts a leader or a follower, the follower is not able to sort it out by itself. It needs to contact with leader, which then will start something that we know as a quorum. So usually it works that way, that once we will receive an update as a leader, we will send it to our followers. And until we get a majority of writes confirmed by those followers, we cannot process further, which introduces latency. And latency can be killing, especially when we are talking about globally available systems, because as you can see here, there is a significant latency when we are trying to communicate between database and data centers living in different continents. Here you can see the round trip times of example connections like that. And keep in mind that in case of leader-based clusters, we need more than one round trip time usually to get to the correct value. So with having, for example, 200 milliseconds of latency with 2 round trip times means 400 millisecond latency. Now imagine that we are sending millions of requests per second, and in this case we will simply not be able to achieve the desired goal. Our system will not be faster as we are adding more servers. Quite contrary, it will be slower. And this is something that we want to solve, because as it turns out, we don't really need a leader to establish one single value. We could simply let each replica let them update their part of the state on their own, and simply synchronize that state with other replicas from time to time. And what is most important, because in this case, when two replicas, for example, have updated the same value, they will find that they will potentially reach a conflict, right? So in this case, we want to be able to resolve that conflict rather than to avoid it, because conflict avoidance is something that leader-based clusters do. Conflict resolution is something that leader-less clusters are able to solve. And how do we do that? So instead of trying to avoid conflicts and solving them using the consensus, we can simply try to build some kind of common understanding of the intention of our updates, of our operations. If we know what the intention was, then we are able to avoid those issues. So there are three key mathematical properties here. Sorry for talking about mathematics, but as you will see, those are useful for us later on. So there are three operations basically: commutativity, associativity, and idempotency. First two means that whenever are we sending an update from one machine to another, and we have multiple of updates, it don't really care if we send those updates in correct order or not. And this is the great property that we would like to achieve, because if we don't need to care about order of updates, then we don't need consensus. And third property, idempotency, is something extra, which means that we can send the same update multiple times, for example, to make sure that it reached the destination. And we don't need to worry that it changed the state of the system because we send the same update twice, right? And it turns out that in mathematics, for example, if we think about the simplest operations, there is not many operations in mathematics that could achieve that, but there are some. For example, is number addition solving all of those properties? The answer is no, because, well, while number addition is commutative and associative, it's not idempotent, because, for example, if you add 1 plus 1, we don't get 1 in the result, right? But it turns out that there are two properties that we will use in practice that maintain those properties. One of them is set union. So when we have union of two sets, it always maintains those three properties. And another one is maximum of two numbers. So minimum as well. But in case when we are trying to get maximum of two numbers, we'll always maintain those properties. And why does it matter? So let's try to build this distributed view counter that we were talking about at the beginning. This is the JavaScript code that pretty much does it. So the idea here, I will go back to this code later. The idea here is that we have a map where keys are the unique identifiers of our replicas and numbers are partial view counters. So basically, each time we are sending an update to a replica, it's only incrementing the number of the counter that it owns for itself. Now, since every replica has this partial counter number, if we want to see the global amount of views that we observed in the entire space, we just need to sum those numbers together. And this is resolved by the operation that you can see here in the highlight. Now there is an extra thing called merge operation, which is designed to solve the conflicts between different replicas. So basically the idea here is that we will take the state, serialize it, send it over the network to another server, and resolve all potential conflicts by merging this serial remote state with the local state on the server and getting the final state in the result. In this case, we will be taking a max of 2 G counters, which means that basically we are taking key value pairs pairwise with each other and take the maximum values of those. And why does it works here? Because G counter, as the name suggests, growing only counter, is only incrementing its value. So whenever we will see that we have a higher value for a given replica than the one that we see locally, we can be sure that this value is more up to date, because this counter value cannot, go down at any point in time. It can only grow. And this is a very simple trick that works and will work for this case for our growing view counter. And this is realized in the highlighted code that you can see here. This is where we simply applied mathematical operation to get some real life results. And this code, you could use it in this Azure Cosmos DB example I've talked about before. Now, let's take another example. Let's say that we would like to have a like counter, right? So we will, unlike the view counter, we would like not only to increment it, but also to decrement, because if we like something, let's say, for example, some post or video, we would like also to cancel that like. So we need to be able to unlike this. So how to count those values in this case, right? We talked about growing only counters, that they can only grow, but here we need to decrement this counter number as well. So let's use composition. Let's say that we'll have 2 counters. One will count increments every time we would like to add something to it, and other will count decrements. So every time we will cancel our like, we'll use the decrement on the counter responsible for decrements. In this case, our global value will be a value of all increments minus value of all decrements. And this is practically it. We weren't able to basically decrement those values on the G counter side, but we can have 2 G counters, which will be, each of them will be growing in their own direction, but the total number can go up and down as we need to. And in this case, merge will also be simply merging of the 2 corresponding increments and incrementing and decrementing counters. Now, another use case. Let's say we have voting systems when we would like to say that one person can vote, but he or she can vote only once. So it cannot add more votes that it wants to, and then he or she wants to. But on the other side, we don't want to know what exactly he or she voted for, right? Because this is what privacy in voting systems means, right? We don't want to know exactly who voted for what, but we want to be able to say that this person already gave their vote and should not be able to vote again. So this is simple, because we can see all of the voters using a so-called G-set, growing only set, and in this case it's simply a set. So whenever a person gives their vote, we can basically increment or decrement, increment the counter for the option they voted for, while at the same time use this G-set and add them to it, so we know that they already voted, even though we don't know what they vote for. Now, this G-set means that it grows only. So again, we cannot remove element once it has been added here. But at least in case for the voting system, it doesn't really matter, right? Because if somebody gave their vote, they cannot, take it back. You cannot go into the box and pick up your vote again. This is not how voting works in this kind of systems. So it's not a problem really here. However, sometimes, oh yeah, and merge operation is simply a union of two sets. So we are serializing set from one replica, deserializing it on the other replica side, union those two sets together, and this is the way that we are resolving conflicts. And again, this is safe simply because we can only add elements to those sets. So the case is that we would like to also be able to sometimes add or remove elements, and in this case we have something that we know as distributed shopping cart. So this was actually first practical example of serialities used in the past, because when Amazon created the shopping cart service, it worked exactly this way, as a distributed shopping cart using serialities. So let's say, for example, that you are adding some items, some orders to some products to your shopping cart, and you are taking your cell phone or something like that and going into the basement to check if there is something more to being added, right? So you have this cell phone in your basement, you've lost the connection, but you are still want to be able to operate on it. You still want to be able to add or remove elements to your shopping cart, hoping that when you will be up again, connecting to your local Wi-Fi, you want to be able to see all of those updates. Maybe your wife or husband in the meantime tried to, update it as well while you were in the basement. So you want to be able to solve those conflicts that could appear from that automatically, because, our customers are not distributed system experts. They don't want to care. They don't care about that. They just want it to work, right? So how it could look like? Well, since we know that we could operate on the sets and counters in distributed manner, we could think about maps. So where the key is the name of our product and the value is the counter saying how much of the quantity of that product do we want to buy, right? So in the previous example of gset, we already used that map concept as a set. Simply, if you will see it back, here we also have a map. When our item is the key of that map, just element and just the value was always 1, because in case of gset we didn't use it. It was not necessary there. But in case of maps, we can simply add new elements and use the value part of that map to be a counter, in this case incrementing and decrementing counter, so positive negative counter that we were talking about before, to compose our gset with pn counters as its value into something that is called gmap, so growing only map. In this case, our value will be simply a number of items, a map of items with the values being values of the pn counters. And for example, if we incremented and incremented them enough number of times, it will be 0, so we can simply discard it as being not displayed, right? Because it's 0, so we are not interested in it. And this is another example how can we combine the existing concept that we are talking about gradually into more and more complex data structures. Okay, so if we want to add one element to our shopping cart, we can simply add an item, and in this case, in this code that you have highlighted here, ID is simply an identifier of the replica we are sending, we are right now in. So let's say, for example, that our replica numbers are the identifiers of the zones that we are in. So for example, let's say this is Amazon East Cloud 1 or something like that, right? This is the identifier of our current replica ID. The case here is that those replica identifiers must be unique. So, we don't ever try to clash two different servers trying to update the same position at the same time. This is why those identifiers should be unique for each replicas. It could be, for example, identifier of device. It could be identifier of the machine. It could be IP number if you are able to, say that this will be only unique for the entire life cycle of your system. So yeah, we already talked about values, how we are constructing them. And solving the merge conflicts is simply iterating over the keys and values of those two replicas that we have, two maps, pairwise, adding the keys together and solving the value part of them using those PN counter merge, because we can compose merge of more complex data structure out of the merges of the simpler data structures that we were using here as internals of this system. Okay, so another example, because in this case we were using growing only map, so this map could only grow, but again, this is not something that we always want. Sometimes we would like to be able to add and remove elements from our set of items, for example. And this is the great case, for example, for Twitter, when we have list of followers for each person. And we would like to be able to follow and unfollow this person, right? So we need to be able to add ourselves there to the set of the followers and remove them from it as well. So in theory, our gset could only grow and had no safe semantics for removing values. But if we compose two gsets together to be, two gsets, just like we composed two gcounters, could we be able to add and remove values just like we incremented and decremented counter? Yes, but with a little catch, because in theory, we could create this set where we have a set for elements added and set for elements removed, and our value in this case would be simply every element from the add set that hasn't appeared in the remove set. It's also called tombstones from time to time. So in theory, we could, of course, create something like that. It is very analogous to this positive-negative counter example that we have at the beginning. But there is a problem that once we remove that element, we couldn't ever insert it again because it's already in remove set, right? We cannot remove it from remove set. And another is that those tombstones needs to be persisted potentially forever. And this was exactly the case in the SoundCloud, which is no longer there, I think. But they were using CRDTs for the list of the followers that they were using on their site. And at some point, the JSON that they had there that were tracking all of the remove observers could be, for example, 2 megabytes, while the actual number of followers could fit into 5 kilobytes, which is a huge number of tombstones to be remembered and dragged along with all of the data that we have there. So we want to avoid that. So one thing to do is simply to add the timestamp. You remember that we had this map that was used for our gset, but the value part of that map was not used. It was only set to 1. What if we would use it and, for example, set a tombstone of the time when we had added this value? Now, when we would like to insert a new value, we create a new entry, add it to the add set with the timestamp when this element has been added there. Now, if we would like to remove that element, we can simply remove it from the add set, because what is important here is not if it exists in the set of adds or removes, but if we remember that it ever existed. So in this case, it's safe to remove C from the add set because it will be added to remove set with another timestamp, the newer timestamp. And in this case, we could of course add it again. And again, remove it from remove set and add to add set with the higher timestamp. And in this case, we could create something like last write win set. So the most recent timestamp is the more important, and simply say that our final list of followers is all of the followers from the add set which had a timestamp higher or equal, depending on our semantics, higher or equal the corresponding values from the remove set that had lower timestamp than the one that we have in the add set. So we know that we added the element after it had been removed somewhere else, for example. Okay. So this is the example code. You don't need to look at all of it at the moment. And here I was talking about timestamp as in the simple date time now from the .NET API, for example. So we will simply take a current timestamp that our clock gives us. But this requires two things: that our clocks have to be in sync. So it doesn't always happen. Sometimes it's like different servers can have different time values, even if we are counting the UTC time, sorry. And those values can drift away from each other, even for something like, for example, a minute. Also, if we would like to have something like that on the mobile devices, where we don't have a control over the user device, this is even more dangerous because, for example, somebody could say that his updates will always be winning in case of competition happening, simply because he moved his clock on his cell phone a month ahead, for example. So his timestamp will always be the highest. And this is not fair, and this is something that we would like to fight with. And another thing is that we cannot discover if two updates knew about each other when they were happening. And this is something that we would like to fix, and this is where vector clocks comes in. So a vector clocks look very much like the G counter we were talking about before, but they also add some extra operation, which is comparison. We didn't talk about comparison in case of G sets, but we can talk about them in case of vector clocks. So a vector clock has 4 instead of 3 different comparison options. So if all of the corresponding key value pairs have the equal values, we can say that these two clocks are equal. If one of them, at least one of them, had higher value than another, that we can say that this vector clock is greater than the corresponding part. In the same analogy comes to lesser than, but the most interesting part is what if some of the entries have values higher and some of them have values lower in the corresponding entries, right? This gives us information that those two values were updated on 2 different replicas in the same time before they were replicated to each other. So those two updates didn't know about each other. And this is why we can detect concurrent changes and react to them accordingly. So this is the implementation of this comparison method. I'm not going to go over it because, sorry, we won't be able to talk about all of it at the moment. So we could improve our remove observed set by using this timestamp, which is a vector clock instead of date. And this would require us to set some specific semantics about updates, like what happens when we detected the concurrent update? What should we do in that case? Well, we can say that either if we detected that the value has been concurrently added or removed, either one of two can happen. We keep the value as added or we keep the value as removed. In this case, the code you can see here, we treat that added value will always win over the removed one. So if 2 people will concurrently add and remove the same value from our set, the value and the one that have added it will always win. Okay, I will need to cut some of the pieces from here. You will be able to probably see it later. So the problem with vector clocks is, of course, their overhead. And this is where the delta would come in, but since we are out of time, I think that we'll we will have to skip that part, and this is it. So thank you very much.